All right, so let's look at section. We are busy with chapter 4, and we're busy with section 4.2, which is all about I/O bit manipulation. Now, if you remember correctly, we mentioned that with the 8051 and the application of it, we use it in a process control environment, and that is where we need to control equipment that's on the plant. For example, the motor that we always talk about, you want to start a motor or you want to stop a motor, and for that we use the I/O port, because that's really where the strength of the 8051 lies, is with the I/O port. So let's look at bit manipulation then, how we're going to handle the I/O port. And in this section, we will further examine the 8051 I/O instructions, and we're going to pay special attention to I/O bit manipulations, since it's a powerful and widely used feature of the 8051 family. Right, now all the I/O ports differ on all the different 8051s, and that's usually where you will decide what size of 8051 family you're going to use, which will be determined in terms of the I/O ports that you're going to need. Because obviously the more I/O ports you have, the more expensive the 8051 is going to become, isn't it so? Right. So you will, for the example we used with the gate motor control, where you would only maybe need 4 I/O ports, then you're not going to use an 8051. That's why they use a PIC there, because it's going to be much cheaper. You always got to think you're going to produce something, and you can't. I mean, 10 Rand on one difference is not a lot, but if you start making 1,000 gates times a 10, then it becomes a lot of money. Okay, so you'll specifically know what is your application, and according to that you will see your ports, how many ports you need. Now, sometimes we need to access only 1 or 2 bits of the ports instead of the entire 8 bits. Now, that also makes it powerful, because on some of the controllers, you can only access the 8 bits at one time. So you can't program individual bits. That's it, you're stuck. But with the 8051, you can select either one bit that you can address for output or for input as well. Now, of the 4 81-bit ports, we can access either 8 bits or single bits, as I said, and there's the instruction that does the bit addressing on the port. So obviously we can say set B, which stands for set bit, and then P is the port, we're talking to the port, and then X is which port, because we know the 8051 has got 4 ports. Now we're going to mention, okay, which port do I want to talk to? So let's say, for example, it will be port 1, so the X will become a 1, dot, and Y is a specific bit of that port. So it can be dot 7 or dot 6, depend on how you've designed your circuit and which port is connected to the motor. Now, for this example, set bit port P1.5 sets high bit 5 of port 1. And always remember that we start at data bit 0 going to data bit 7. That's how we label it. Okay, we don't start at 1. And then, for example, the following code toggles P1.2 continuously. So, what do? We want a certain bit which is connected, for example, to a LED on your development board, and we want to toggle that bit on and off all the time. So we're going to write a 1, and then we're going to obviously write a 0. How do we do that? First of all, we can use the instruction complement, because what does complement do? Complement is the same as the inverter function. Yes, it will. If it was a 1, it will make it a 0, and if it's a 0, it will make it a 1 again. So let's look at this little program. I will complement port 1.2. Now, this is just a general little program. Obviously, they can state if it's a program you have to write for the exams. Then they will say, okay, you must first start off with port, that specific port 1.2 being a 1. Now we just complement it, because they don't say if it was a 1 or a 0. Now, usually we can say that when the thing was on, it usually will be a 1. Our ports are all a 1. So I'll complement it. So whatever it was, it's going to go to the opposite. Then I call a delay. Why do I call a delay? Because if you're just going to complement all the time, you're not going to see the LED flashing, because that's really what we want to do. We want to see the LED going on and off all the time. So what will we do? We need to call a delay to make it slow, because as we know, the microcontroller runs quite fast. So I will call, and we've discussed the call. You remember we've discussed the call instructions, isn't it? A call stands for absolute call. So that then we can run in the 128 bytes of RAM we have available. So we do a call, and we call delay. Now delay is obviously a routine with the name delay. We don't show it here, but that's what we discussed already, the delays that we make with a loop. Then short jump to back, and I complement again, 1.2. Here's an example of the again program. It's just a simple delay. Right. Oh, that's another variation of the buff program, but this one is the best one, it's a shorter one. Then I short jump back, and I complement it again. So can you see it's going to toggle? The time that it takes to be, that's going to take to toggle, is obviously depending on the delay program, isn't it? Okay. Now you can set the delay depending on what they ask you in the exam to do, or in your application, that it must be on for 1 second and must be off for 1 second. Or it can be on for 1 second and off for half a second. Then obviously you will use 2 different delay programs. Here's another way of doing the same thing, is if you don't use the complement. Now once again, always we try and be effective as possible with our programming, but this will also give you the same result. I can set the bit, because that's the instruction we discussed there, 1.2. Now the difference is between this program and that one is that I start off with a 1 now. So as soon as my program starts to run, it's going to be a 1. But if you say complement, obviously you don't know what it was. You can assume, but we also said that in programming, never assume. Right? So then we will call the delay. Then I will clear the port. Right. I will clear the port, and then I call delay again, and then I short jump back to again. But you can see this one will take more memory space, isn't it? Okay. But once again, it's not a crisis if you start learning programming, as long as you get to the result and you understand the logic behind it, then it's not a problem. Okay. But always try and be the most effective in your programming as possible. Then this is just a table showing the layout of the ports, how they are numbered. So port 0.1 and port 0.0 and port 0.1 and so forth. So that's a labeling that you will use when you use the set bit or clear bit instructions. As another example that we have to, they want us to write a program, create a square wave for 50% duty cycle on bit 0 of port 1. And we must, in the B1, create a square wave of 66% duty cycle on bit 3 of port 1. Now, once again, now you have to know what does duty cycle mean? You remember something about duty cycle? From digits 1. Right? And the duty cycle is the on time in relation to the period of the pulse, isn't it? I mean, it can be on 100%, it can be off 100%, or it can be 50% in this example. So 50% means that it's going to be on for half the time and off for half the time. That is 50% duty cycle. So they want us to create a pulse that looks like this. And you can see this time and that time will equal to one another. And this is my time t. Now, in this little program, they did not specify how long it must be on. They didn't say it must be 1 second or 2 seconds. But the main thing is it must be 50%. Now we're going to do that. First of all, it must go out. They specified us it must go out on bit 0 of port 1. So, first of all, I must set the bit. Right. So I set the bit P1 0. So I make it a 1. Okay, now this you can always maybe have a dotted line. So now it goes to a 1. This is my set B instruction will take it to a 1. Then, how long is it going to be on? I call a delay. Now that's a delay, let's say, of a half second, what you've written, subroutine. And I call the delay. So this here, This part here is obviously determined by the delay, right? How long that delay routine is. So it's going to be called a delay. That's a subroutine. So we know that if it's completed, the delay is going to come back and it's going to do a clear. As soon as it do a clear, then it's going to take it to a 0. So this part here is the clear instruction. Right? Makes it a 0. And then I call delay again. And which delay do I call? The same one, isn't it? So that means that this is also delay. So that will equal that. How do you change a duty cycle? You will just call different delay programs, isn't it? All right, so you got the idea. They just got another way of doing the program is that we had previously is complement the port. Now with this one, once again, you don't know what it was, eh? Okay, so if you do write program, then you have to be very specific. So you know you can't, especially in doing process control, you can't just assume anything. You got to make sure, because I mean it's a difference between starting a motor or stopping a motor or even causing a big crash. But there's another way of doing it. So I just complemented a long call the delay. There they just use a long call, and then I just short jump back to here again. So this is going to give you exactly the same thing. Okay. But with this program, can I change the duty cycle with this program? No, you can't, because you're just calling delay. Okay. So it's not possible, as with that program, to change the duty cycle. So this one is fixed with 50% duty cycle. And then they want us in the B question, they want us to create a 66% duty cycle. Now, once again, if you think of 66, what is that? 50% is half, 66% is, come, a little bit of math here. 66 is 2/3, isn't it? Very close. Not 100%, but it's 33 gives you 100%, isn't it? So now you can think already, if that is 66%, then it needs to be on 2/3 of the time and off 1/3. So think a little bit. So what am I going to do with the delay? Yeah, you just double the delay, isn't it? For the on time. So you call delay twice. And that delay for the off time only once. Yeah. You see. And there it is. What I just called. So what do we say? We call delay twice. Okay. Now obviously, always, it all depends on how accurate you have to work. Because obviously 33% or 66% does not give you exactly 100%, isn't that? So it all depends how accurate things need to be and how fast, and that's all got to influence. And also, you can have two different delay programs, isn't that? We use the same delay program, but you can have, instead of delay, you can have a delay 1 program, and that one is 66%. Okay. So, but that's exactly what we discussed now, and that's going to give you a 66% on time and 33% off time. Sorry. All right, these are the single bit instructions, because we said we're doing bit manipulation on the port. Now, to do that, we need some different instructions that can do that, and all of them will involve single bit instructions. And there I've got set bit. Set bit means set bit. It's going to make it a 1. And then I've got clear bit, as we have had in that little program there. Then we've got complement. Then we've got jump bit. Jump to target if the bit is a 1, because it's jump bit. That means a 1. So then I jump to target, and target is a label wherever you want to jump to. And then you get jump not bit. Now not, we know in all the digital stuff that we dealt with, as soon as you say not, we know that is a 0. So then if the bit is not 0, then it will jump to the target. And if it is 0, then obviously it will continue, it falls through the program. And then the other one is jump to target bit and clear the bit. So this one does three things. It jumps if the bit is a 1, and it clears the bit. Now that you want to use a lot of times, so that from outside, something set the bit. And then you see, okay, the bit is a 1, but now to acknowledge that, you do it in one instruction and say, okay, I've seen the bit is a 1, so I can reset the bit. Right? And then that, what happened now? And that all happened in one time. All right, there's back. Yes. Yes. Yeah, it's just a label. That's right. Yeah, it's that label there. For example, back. You see, short jump back. You're going to have the same thing. Jump, bit, carry, back, and the target can be back. All right. Checking an input bit, because now remember with the 8051, with the port control, so with the I/O programming, we can send a bit, but we can also get a bit in, right, as mentioned, because you want to check something happened, and you do it for monitoring. So you control something, once again, the motor story, if you want to check if the motor has started, and the way you're going to deal with that, you're going to have some converters that's going to convert the turning of the motor into a 1. And that 1 is going to fit back into one of the pores so that your program can then see, but the motor has started. And so those are the instructions that you can use to monitor the input port. First of all, is I can move any port X to the accumulator. But now PX, that means the entire port. Right. To the accumulator, and obviously then I can do the AND or the OR instructions to check which bits are set and which ones are not. And then I can say jump not bit. Okay, that's the one we're at. So basically jump not bit will be reading from a port because it's checking the port. It's monitoring a specific port. The same with jump if bit on pin 1.2 is high, then there's my target once again. That's what I'm going to do. Now obviously that depends. If it is a 1, I go to the target. If it's not a 1, remember with the programming, it goes through. That's a decision, either one way or the other way. You only can go two ways. Right? And then move, I can also check, I can move Y, okay, to a port. So I copy the status of pin 2.4, for example, to the carry flag. Why the carry flag? That's very handy because we have quite a few instructions that monitor the carry flag, isn't that? So the carry flag is not only used when we do addition and subtraction. You can also use it to monitor. So you'll move something to the carry flag and you can check there. The reason being that there's a lot of instructions that works around the carry flag. And then this is also a good one, is compare, jump, not equal. So that's also a way of monitoring things, is that I take the port and I move I compare the accumulator with port 1 and jump if not equal. So obviously I will have an instruction that will load a value into the accumulator, and I take this value in the accumulator and compare it to the port. And obviously depending on which bits are set, it's going to be either equal or not equal if the value is equal. And then also you make a decision. Programming is a lot about making decisions, isn't it? And that's when you get data from the input, then that helps your program making a decision of what to do next. There's another little program. These programs, I'm not going to run through all of them. You know you have to type that into write. You have write at home, wherever, and in a class, and you have to put those stuff in, and then you call up in the IDE interface your main registers, and you can see how the things are moved to the port. Okay, because it shows you the port, isn't it? On the main registers. Good. There's also a little practical example of assume that bit 2.3 is an input and represents a condition of an oven. If it goes high, it means that the oven is hot. Monitor the bit continuously. Whenever it goes high, send a high to low pulse to port P 1.5 to turn on a buzzer. Nice practical example, isn't it? So where we monitor the oven. So what we'll do, this is showing you the hardware connection on, oh, yeah, I'm hoping it's not going to happen. All right, so we've got a switch, we've got VCC, and we've got a switch, and we've got down to a 4.7K resistor down to ground connected to my input. So this is typical, a practical example of how you would do the hardware connections. Oh, come on port 2.3, that's the input, all right? And then the output that we use here is port 1.5. So we use one of the other ports. So that just goes through an inverter. You'll see now why. And that we use a 74 LSO4. And if you remember from the LSO4, that is a inverter. Yeah, if you didn't remember, you can just look on the drawing there. Eh? So now we check. Now jump, not bit, 2.3 to here. So what do? This is also done a lot in programming because I'm monitoring. So the microcontroller sits there, and that's the thing he can do very good, is that he can sit there the whole day and monitor that port. Better than you sitting there and monitor the port the whole day, isn't that? All right. So it sits there and it monitors this bit. It's jump, not bit. In other words, it's not a 1. All right. Then it sits there. Then all of a sudden it goes to a 1 because this can be a thermal switch because we said it's checking the temperature. Now you know from your instrumentation side, you can have a thermocouple or whatever that's monitoring that, and at a certain level you're going to get a 1 out. Or you can have a bimetal switch, but as soon as the heat, it's a lot of heat, and at a certain point it's going to bend and it's going to make contact. Now that's where your process instrumentation and electronics all kick in. Right? You can't be without that. So then that switch will close. Okay. Now why is there 0 always on that point? Because the switch is open. That's why it's not bit, it's not set. Because there I've got ground, resistor, and port 2.3. So that point is pulled low. It's at my ground level. Then that switch kicks in, it makes contact, and what does it do? It takes VCC, it goes down to ground, I have current flow through there, and what happens across the 4.7K resistor? Yes, you get a volt drop. That volt drop will be then on point 2.3, which will pull it up to a 1. We'll pull a 1, and what's going to happen to my program? My program is saying, oh, it's a 1 now, and it's not going to sit in the loop anymore. It falls through here. So then I set bit 1.5, I set it, becomes a 1, and then this buzzer will come on. It's going to buzzer, it's going to give an alarm. Oh, this is just a simple little example. What it can also do is it can then control something else. So what we'll usually do, this will go out to, because it's an oven, so we can have a control going out to the element, and it can switch it either on or off. Well, obviously it will, because the temperature is high now, isn't it so? So it's going to switch off the element or bring the voltage down or whatever. But there's some interfacing there. And then the temperature will come down. As soon as the temperature comes down to a certain level, that switch will open up again. As soon as the switch opens up again, that thing goes to that output switches off, and it's going to sit in that. You see short jump here again, and it's going to sit there and monitor it again. All right. So that's basically that. And here's another little program. These programs, you must type them into right and call up the main registers on the IDE, and then you can see how it works. Okay. But basically what we do is we just take the status of the port and we load it into the carry flag. And then we've got a little program that just checks the carry flag. What is the value of the carry flag? And if the carry flag is a certain value, then we do something. Otherwise, we do something else. And all they want us is to write the value N or Y to the ports. Okay? Write it to the ports depending on what's happening with the carry flag. Another little example, those examples you must work through. That's all of you, why all of you has got a textbook.